So the next speaker is going to be Eduardo Miranda from UNICAMP, and he's going to talk about the domain wall between a Mott insulator and a metal is an anomalous metal.
Okay, thank you, Alexandre. I would like to thank the organizers for inviting me here, and I'm going to tell you about this work that's been building up for a few years now, about a subject that's not very much explored yet, which is a domain wall or an interface between a Mott insulator and a strongly correlated metal. I'll explain those words as I go along. So this is work done by mainly by these two students, Sung-Han Lee, Marta Viagran, and some collaborators, Darko Tanaskovic, Yaksa I don't know how to pronounce that name, Vlad Dobrosavljevic, my good old time collaborator. So the Mott transition. So the Mott transition is one of the most basic phenomena in condensed matter physics. It's a metal insulator transition induced by interactions. Okay, so generic phase diagram is like this one. For instance, this is chromium doped V2O3, paradigmatic Mott insulator, where you have this line here where there is a first order phase transition between a metal and an insulator. I'll show you conductivity data later. You have actually a region here, but because this is a hysteresis region where you have coexistence between the two phases. But there's actually a single thermodynamic line here separating these two phases here. And you see that it ends at a critical point at a finite temperature here. So these are organic salts where you see this behavior as well. And there are other systems where this is observed. You also notice that at low temperatures, other phases intervene. So you might have antiferromagnetism, superconductivity, quantum spin liquids, and so on. But the Mott transition per se that we refer to is actually this transition at finite temperature, which can actually go down to very low temperatures, for instance, in these organic salts, to very low temperatures here, and before some other phase transition intervenes. Okay, so what's the physics of this transition? The physics, as I said, is due to interactions. So the first condition for you to have this transition is to have one unpaired electron per site. Okay, so if there were no interactions, this would correspond to a half-filled band, and this would be a metal. But because of interactions, if they are strong enough, the electrons will be unable to hop from one side to the other. They will be jammed in their own sites, and this is going to give rise to an insulator, which we call a Mott insulator. So that's the basic physics of this phase transition. And as we saw, if you apply pressure, I didn't emphasize it enough here. This is temperature versus pressure. So you see that whenever you put pressure in these systems, you go from the insulator to the metal. So what happens is, of course, that pressure increases the hopping and effectively decreases relative to the hopping in the interactions, and then you can metallize the system and have a metallic phase. So that's the basic physics. Now, there is a very strong similarity between this phase diagram and the liquid-gas transition. Okay, so the liquid-gas transition, generically, is also a first-order transition that ends at a critical point. And you can actually go continuously from the gas to the liquid if you go above that critical point. And you can avoid going directly through the phase transition. So here, it's the same thing. Okay, you can go from the metal of Fermi liquid to the Mott insulator if you go around the critical point. So as I said, I think Eric mentioned yesterday, the only rigorous distinction between a metal and an insulator is at zero temperature. Because at finite temperatures, there's always excitations. You can always have a finite conductivity at finite temperatures. But as I will show in the next slide, you can clearly see that there is a de facto phase transition as you cross the first order line over there. Okay, so here I want to just bring the similarity between the Mott transition and the liquid gas transition to you. So this is the conductivity data for the V2O3. So for instance, this is the conductivity. I don't have data here for the conductivity below the critical point, but below the critical point, you have a very large drop in conductivity as you go from the metal to the insulator, sometimes 4 orders of magnitude drop, so it's a clear phase transition. But as you go close to the critical point, the drop goes to 0. Just like the density difference between the liquid and the gas is finite as you cross the first order line, but this difference goes to 0 as you approach the critical point. So it's very similar. And what this data here shows is that if you look at the critical exponents close to the critical point, the finite temperature critical point, based on the conductivity data, you find that the transition is precisely, corresponds precisely to the Ising universality class, the 3D Ising model, which is also an indication that it's very similar to the liquid gas transition, which is also in the same universality class. So you can actually look at the exponents. If you're far from the critical point, you get mean field exponents, which tells you that mean field theory is actually pretty good. But as you get very close to inside the critical regions, then you recover anomalous classical Ising exponents, and there's a very good correspondence there. So there must be some scalar order parameter behind this, just like in the Ising model, and just like the density in the liquid gas transition. And this is actually known, I'll talk about this in a while, that you can define a scalar order parameter that governs this transition. There's actually different ways of doing that. Now, there's a very good description of this transition with a theory that's been called dynamical mean field theory, or DMFT, that I'll try to explain very briefly in one slide. So first of all, that physics that I showed, schematic of one site, one electron per site and interactions, is captured by the hydrogen atom of models in condensed matter, which is the Hubbard model. It's the simplest model that you can write down for electrons that interact with each other. So you have a hopping term between nearest neighbors, for instance, and the local Coulomb interactions between the electrons. Now, dynamical mean field theory. So this is by now a pretty old theory, which is appropriate for treating strongly correlated systems. And it is basically the following. First of all, it's a local theory in the sense that the self-energy that governs the behavior of the electrons, the self-energy that comes into the one particle Green's function of the electrons, you assume that it is local. This is the most basic assumption of the theory. So in K space, it doesn't depend on K. It's completely local. And you can actually, just like in the mean field theory of the Ising model, you can justify this approximation in the infinite dimensional limit where it becomes exact. But of course, I'm not going to apply it to an infinite dimensional limit, so it's going to be an approximation. Now, what you do is the following. You focus your attention on one side of your lattice, and you sort of mimic the rest of the lattice as a sort of a bath, a reservoir of electrons with which this single site can exchange electrons. Electrons can hop in and out of the site into the bath of the other sides of the lattice, okay? And then you solve this problem, the problem of one single interacting site that can exchange electrons with a reservoir of other electrons. And this defines a single impurity, an interacting single impurity model, actually an Anderson single impurity model. And then you try to solve this model with some technique. This is the hardest part of the technique, is to solve this interacting impurity model. You can use quantum Monte Carlo, perturbation theory. There's a whole list of methods for solving that model. And then from this solution, you get the local self-energy. And then you impose self-consistency. Okay, so you impose self-consistency in the sense that the bath is formed from sites which are identical to the site that you focused on to begin with, okay? And with that, you have a full self-consistent theory that's, of course, as I said, approximate, but as I said, it captures very much the behavior of the Mott metal insulator transition. You have a first order line ending at a critical point where you go from, here is interactions here, so the at small interactions you have a metal, at large interactions you have a paramagnetic insulator, and at low temperatures you can also describe some of these ordered phases, but this is not going to be the focus of this talk, okay? Now, what I want to talk about is not the clean system, okay? So this is another one of those paradigmatic systems where you have a Mott transition, VO2. And this is scanning infrared microscopy data on VO2, which is basically a way of measuring locally the local conductivity at small regions of your sample. And as you can see here, as you change the temperature and across the phase transition, you see very clearly that there are bubbles of metal and insulator that coexist with each other. So, okay, so this is basically the conductivity. So this is low conductivity, this is large conductivity. And you see that there are regions which are more red and regions which are more blue. So you have domains of Mott insulators coexisting with domains of metals. And of course, there's going to be interfaces between them. This is for V2O3, the kind of system that I showed before. Same kind of data. And you have the same kind of patches of different phases coexisting with each other. Okay? So you see very clearly here these patches. And I call your attention to the sizes here. So this is very large. These are very large domains coexisting with each other. This is micrometer sized. This is not microscopic. This is very large. Okay? Okay. Now, of course, to have inhomogeneities, you have to put disorder. Disorder will tip the system that's at the critical point or at the phase transition to one side or to the other, depending on the local value of the parameters. So the easiest way to do that is to assume a disordered Hubbard model where you put some random on-site energies distributed with some distribution. It doesn't matter too much which kind of distribution you use. This is what I'm going to talk about is for uniform distribution of site energies. So now you can do sort of an extension of dynamical mean field theory to incorporate disorder. Okay, so this has come to be known as statistical dynamical mean field theory, but the spirit is the same. So you once again, you assume local self-energies. Okay, first of all, there's no K anymore. The system is not translationally invariant. So you have to look at on the basis of sites. And you also assume that the self-energy is local, but now it can fluctuate because of disorder. So one side the self-energy is one thing, and the other side the self-energy is something else, okay? Because they're going to be different. It's a disordered matrix, okay? So, so pictorially you might think of, sort of if you think of the self-energy as the size of those circles, this is the best I can do. I'm not a very good artist. You have small circles and large circles like that, depending on the environment where you are. And then you can do, the rest is basically the same. You solve the problem for this site in the path of the other sites. Okay, this is the hard part. And then you impose self-consistency. But note that as you impose self-consistency now, the sites are not the same. Okay, so the environment of this guy are these other guys here. This is a much, much tougher problem to solve. You basically have to solve one single impurity problem per site and then impose self-consistency. Okay, so this was the nightmare of my student. The theory is exact at u equal to 0. It's a non-interacting problem, a disordered non-interacting problem. That includes, if you are careful, to solve it, even localization effects. With no disorder, you recover dynamical mean field theory. And as I said, one single impurity problem per site that you can solve with some technique. Okay? Now, So you can do that for the disordered Hubble model. So this is the kind of results you have, full-scale calculations for 20 by 20 two-dimensional square lattices. This is a lot of work, as I said. And you can see, first of all, so this is the imaginary part of the local Green's function is a measure of metallicity as opposed to insulating behavior. So when it's large, you have a metal. When it's small, you have an insulator. You can clearly see that as you crank up U, you go from the insulator to the metal, but you have domains, you have large domains, and you have interfaces between them. Okay? So StatDMFT shows these mesoscale space fluctuations with large bubbles of insulator and metals and large domain walls between them. If you sort of define the middle of the road here as the green color, you see that the domain walls, which are the green regions, are very large. You can also sort of zoom in on one single domain wall, and you can define a one-dimensional problem across that wall if you assume that these are very large bubbles. And you can solve this one-dimensional problem to have a closer look at the domain wall. So we did this. This is the phase diagram that I showed before. This is the first-order line. And we did this for different trajectories, but I'm going to show data for looking at along the first-order line, the green line over there. And you can see the domain wall size becomes very large, close to the critical point, as you expect, because they have a correlation length that's diverging at the critical point. And so this is the inverse of the size of the domain wall. It goes to 0. In other words, the domain wall becomes very large at the critical point. It also goes to 0 at 0 temperature. This is a feature of this particular treatment that I'm not going to go into. And there is physics in this divergence here, but I'm not going to go into here. The important point is that if you're close to the critical point, you have large domain walls. So what I'm going to talk about in the rest of my talk is what is the physical nature of what I call domain wall matter. So we know what the insulator behaves like. We know what the metal behaves like. My question is, what does the domain wall behave like? Okay? Is it insulating, or is it metallic? Or is it something else? That's the question. So to do that, I will bring back the analogy with the liquid gas transition, where you have a very good description with a mean field description with Landau theory, where you have the so-called Landau functional. When R goes to 0, you go through the phase transition. You have the quartic term. You have a term that penalizes spatial fluctuations. And you can solve this model, this Landau functional. In other words, you can minimize for phi, the order parameter phi, as you cross from one phase to the other. So this is the Landau potential. This is one phase, the ferromagnetic phase, pointing down, pointing up. And if you cross from one to the other, the order parameter goes from -1 to +1. This is a solution of this equation. It's actually an analytical solution. And you have a domain wall between them. And the point that I want to draw your attention to is the following. The domain wall center is the maximum of the Landau potential. So the stable phases are the minima of the potential, but the domain wall center is the maximum. It's the unstable solution to the Landau functional equation. Okay? So bear that in mind as I go along. So the Mott transition also has a theory that a Landau theory. You can write down a Landau theory for within dynamical mean field theory for the transition. And what I'm going to show is that domain wall is the unstable solution. So this is the part where it becomes very technical. I cannot explain it here, but the actual order parameter, the full order parameter of the dynamical mean field theory is a function, not a number. It can be the Green's function. It can be the self-energy. I took the Green's function here. You can write a Landau functional for that function, okay, G of I omega. And then if you find the minima, you get the two phases. If you find the maximum, you have the center of the domain wall. So the challenge was to find the G of I omega that solves the unstable point of the Mott transition. This is very, very hard to do numerically, okay? But it can be done. It's hard, as I said, but you can find the unstable solution using, this is also tricky, complicated. Basically, you use the Broyden's method, which is a well-known method for finding minima or maxima of functionals. And I'm going to, so this is, we can construct the free energy, and you can see that there are two minima, insulator and metal, and you can focus on the unstable point, and I'm going to show the behavior of that unstable point once again. Well, actually, in this case, I'm going to go on a vertical trajectory. In other words, fixed U, and I lower the temperature as I go inside, as I cross the phase transition from the insulator to the metal, or the other way around, okay? So the first thing we did was the following. You can use dynamical mean field theory to calculate the conductivity of the metal, the insulator, or the unstable solution, the domain wall center. These are the formulas. I'm not going to explain that. This is standard in dynamical mean field theory. So what you see here is the following. So for the metal, here's the resistivity, it goes down. For the insulator, it goes up. And for the domain wall center, it's sort of in the middle, but it goes up. Okay? So these are different methods for solving the impurity problem. Let's see here. Yeah, okay, so usually, for instance, in this QMC, quantum Monte Carlo method, you generate data on the imaginary axis. You have to do some sort of analytic continuation to the real axis. So these are different methods of doing that, which is why there are two curves in these plots here. This is for perturbation theory. This is for quantum Monte Carlo. Both have roughly, they are different, of course, they're different approximations, but they are roughly the same kind of behavior for the metal, for the insulator, and for the domain wall matter. Okay? So the unstable solution has a resistivity that increases as T decreases, but it's not really like an insulator. Okay? There is this thing here that I didn't emphasize too much, the so-called Mott of a regular limit of transport, which means that when the mean free path is equal to the lattice parameter, this is the largest resistivity that you can get in a semi-classical description. This is called the Mott of a regular limit. So you cannot scatter on a length scale that's smaller than the lattice size, than the lattice parameter. And what this shows is that the resistivity in this domain wall matter goes above the Mott of a regular limit, which is a very non-classical, non-trivial behavior. Okay, now the other thing you can do is you can plot the density of states at the domain wall center. This is for, okay, so actually for the three phases, the metal and the insulator and the unstable solution. The unstable solution is the green curve. What you see here is that even at low temperatures, you still see what we call a quasi-particle peak. You see in the metal, you have a very well-defined quasi-particle peak. These are the quasi-particles. These are the free carriers of the strongly correlated metal. But even in the unstable solution, you have a very small peak there. Okay? In the insulator, the peak is gone. Okay? You open up a Mott gap, and the peak is gone. But even in the unstable solution, with both temperatures here, you still see a small peak in the middle. Okay, so what we did was the following. If this is a peak, let's try to describe this as you would a normal Fermi liquid quasi-particle. So a quasi-particle in a Fermi liquid, it has a Green's function that has this behavior. This Z is the so-called quasi-particle residue Z. There is an imaginary part that gives you the scattering time or scattering rate that you can calculate. All these things can be calculated from the self-energy that you got from the solution. So now, if you look at these parameters, so this is basically a Fermi liquid parametrization of the Green's function. You have a quasi-particle residue. In a Fermi liquid, this is a constant. And you have a scattering rate that in a Fermi liquid should go like T squared as a function of temperature. Okay, this is a normal metal. So if you look at the metallic solution, Z goes to a constant, gamma has a t-squared behavior, as you would expect. But now if you look at the unstable solution, Z actually decreases to 0 as a power law. Very, very strange, not a Fermi liquid. And gamma increases with square of the temperature. Okay, so if you try to describe the peak as a quasi-particle peak in the usual way, you have the normal behavior for the metal, but you have a very weird behavior for the domain wall center. Okay, so this is telling you that domain walls matter, as I say, is very anomalous, which is why in the title I said this is an anomalous metal. Okay, there are some interpretations of this kind of behavior, but not going to go into that. So in conclusion here, I think I went over my time a little bit. I talked about the homogeneous Mott state with large domain walls, and I focus on the physics of the domain wall matter, where I think I try to convince you that this is a bad metal, or a non-Fermi liquid, as it's called. And in the future, of course, the challenge is to calculate transport for the full inhomogeneous metal, which I didn't do. I calculated sort of the local conductivity. I looked at the metal bubble, at the insulating bubble and domain wall, but I didn't calculate the bulk conductivity of this inhomogeneous system. This is a real challenge, even within this theory, and this is work for the future. Okay, that's it. Thank you. Sorry for the...
Questions as I go up there? So I have a quick question before. So two quick questions. In the phase diagram that you showed from Kotler, the Physics Today one, so is there from dynamic mean field theory, is there a place where it fails, or is always kind of qualitatively correct?
Fails in what sense?
I mean, you get the wrong phase or is always qualitatively correct?
No, it's always like this. Of course, depending on the way you solve the impurity problem, these lines are at different points, of course. But you have you can have, as CTQMC, probably state-of-the-art method for calculating this. You have an excellent curve. There is one important question, which is where this line is inclined, whether it's like this or like that. That's an important question, just like in water, right? Whether it's this or like that. And here, it's interesting because if you do an extension of dynamical mean field theory where you go from one side to a cluster, you change the slope. And this is known. It's known, the physics is known. Because in dynamical mean field theory, you neglect spin correlations, basically. So if spin correlations between sides are very small, as in a frustrated model, for instance, a frustrated lattice, then you get this inclination, this slope here. If you do the extension where you take into account, because you do the cluster well, you solve the cluster exactly, then this thing goes this way. It's basically an entropy energy consideration that tells you that as you go up in temperature, you go from metal to the insulator, or the other way around. Okay, but other than this, it's a well-defined problem with a well-defined answer and so on.
The other question is, how many sites do you use in your calculation? So you do really brute force, in the statistical one, you do brute force.
Brute force, finite lattice, yes.
On each site you solve the DMFT.
Yes,
so
a nightmare, complete nightmare.
I know.
Now, for the other case, we found the bulk solution for the metal, for the final part, the bulk solution for the insulator, and the unstable, the bulk, it's not a bulk, but the unstable point of the Landau functional. This is in the thermodynamic limit, it doesn't have sizes.
First of all, congratulations for your interesting talk, Eduardo. I have a question about the domain walls. You interpret the domain walls through the Landau theory, and you discovered it is an unstable solution. So my question is, how can the domain walls be so large? It seems counterintuitive for me because it's an unstable solution. it would be intuitive
If you take an Ising model and you go close to the critical point, it's going to be large also. This is just a reflection of the correlation length. It's governed by the correlation length. You can think of the metal as a boundary condition. And then you put a metallic boundary condition to your problem, and then you find the insulator, or vice versa. And that's going to reflect the correlation length and of the phase you're looking at. And as you go towards the critical point, that diverges. So it's completely expected.
Well, first of all, congratulations for the excellent talk. Okay,
Thank you.
I learned a lot. Why don't you take into account disorder in the interaction, U-turn of the Hubbard model?
I could.
You could.
Yes, I could.
Results might be different.
Might be, yes. Absolutely, absolutely. For instance, you can understand this data just like dynamical mean field theory is an Ising model, basically. It's a fancy Ising model. If you put the disorder that I put, this is the random field Ising model, which in 2 dimensions has no transitions, Imry and Mott. And this is consistent with what we see up to the lengths we can go. So we see, for instance, this is as a function of size. So you start with a metal here, then you start increasing. That metal is still there, but then you start getting the other phase. If you go further, you're going to generate the other bubble, and in the thermodynamic limit, there is no transition. Okay, this is an effect of finite size in 2 dimensions. In 3 dimensions, there is a transition in the universality class of the random field Ising model. If you put in the U, it's a different universality class, not the random field anymore. Okay?
So, Eduardo, so the disorder is just for clustering the phases, for seeding the 2 phases, or does it play a special role? Or my guess is in the same line of question.
It's the same question, yeah. It's a random field Ising model, so you favor up phase here or a down phase there. So it's because of this, so you have, it's a rare region, in fact. You have a rare region of up phase and a rare region of down phase, and you have a domain wall between them. And you nucleate one or the other, and you have a domain wall between them.
So well, why go this brute force and have this random field? And you could do the same thing by choosing something way simpler, right?
That's why we did here. So this is, we take a 1-dimensional thing. We could do a 3-dimensional thing where we put a bulk metal here, a bulk insulator there, and you see what happens in between. That's what I told that guy. You could do that. We did that. Yes?
First of all, thank you very much for the very interesting results. My question is a bit more general. So people usually, in cuprates, for instance, they use the Hubbard model to describe them. So we know that cuprates, they have different phases as you dope them. Doping them like with substitutional dopants, that introduces disorder. My understanding is that people usually ignore disorder in the treatment. Can you learn anything like about the strange phase?
Absolutely.
With this, okay.
Absolutely.
Can you comment, please?
It's next in line.
Okay, thank you.
And of course, if you do a good job there, the phases are much more interesting than just. The Mott insulator in the metal, you have pseudo gaps, you have other stuff. We plan to do that, but it's tough.
I have a quick question. You're using dynamical mean field theory, and you should have a crossover to the actual critical behavior of the system. Do you expect any change in the properties, the anomalous properties of the domain walls?
What exactly do we mean by a crossover in this case?
As you mentioned, for instance, for the Ising model, you have mean field exponents at some point, and as you get close to to the critical point, you have a crossover for the...
Yes, yes, the critical phase, right? The critical region of the transition. Yes, that's what's shown here. The point is that, well, this is experimental result. It's very small critical region. You can see here. So this is the mean field exponent. To get this beta, this is beta equals 1/2. This is mean field. To get beta 0.34, you have to really zoom in on this thing here.
It's like a superconductor, okay.
Yeah, it's like a superconductor. It's a very small critical region, okay? Now, in our case, we cannot go beyond, we cannot really do a good job of the critical region, because that would mean taking an infinite cluster. Sorry, I can't do that.
Okay, let's thank Eduardo again.
Thank you.